Here in Thalheim in Saxony-Anhalt, Q.Cells started producing high-performance solar cells in the summer of 2001. The audacious vision of the company founders laid the foundation for what is today a rapidly expanding company with one of the largest and most modern production facilities worldwide. The development of new cell formats and ongoing optimization of the production processes are setting new standards for the entire industry and turning Q.Cells into the leading independent manufacturer of photovoltaic cells. Renewable energy sources will dominate the energy market of the future. Photovoltaics, or the direct transformation of light into electricity, will play a particularly decisive role in this regard. Here in Thalheim, high-performance solar cells are created with clearly defined performance features. Q.Cells occupies a key position in the value-added chain of the photovoltaics industry. Q.Cells refines the raw wafer to create solar cells of the highest quality, which are then further processed to create solar modules. The solar cells are created from the raw wafers, from multi- and monocrystalline silicon. The wafers undergo a quality test to ensure that they are the correct size and weight and are free from any damage on the edges or surfaces. They are then conveyed to the wet bench. Here, any residual chipping is removed from the raw wafers in a wet chemical process. The wafers are then cleaned prior to further processing. They undergo automatic etching, followed immediately by rinsing in different basins. The raw surface of the wafer is removed in the etching bath, which contains caustic potash solution. Following this, the wafers are dried. A solar cell consists of a large surface p-n transition. In order to create this, an N-conductive surface layer is attached to the positive conducting blanks in the diffusion oven at around 900 degrees with phosphorus gas. Because the plastic magazines would melt in the oven, the raw wafers are transferred onto the process boats made from quartz. The wafers are exposed to a phosphorus-based atmosphere in the oven. The high oven temperatures cause the phosphorus particles to diffuse into the wafer. This in turn causes the water surface to convert from a positive to a negative conduction type. To check the diffusion process, the layer resistance of every cell is measured. The phosphorus silicate glass, which is created as a byproduct during diffusion, is removed in a second etching bath. To ensure that as little solar radiation as possible goes missing, a layer of silicon nitride is attached to the cell. This gives the cell its typical blue color. Before being coated, the cells are transferred into Sigrabond trays. In a plasma-reinforced vacuum process, the reaction gases ammonia and silane are separated from the surface of the wafer in the form of silicon nitride. The fully coated cells are transported further along and their color is checked by a camera. In order to extract electrical energy from the solar cell, contact grids made from silver paste are attached to the cell using screen printing. This is what causes the characteristic grid pattern to appear on the front of the cell. The reverse side also receives two contact strips made from silver paste as well as a layer of aluminum, known as the back surface field. This works like a sort of mirror on the electrons. Then, in the furnace, The contact strips are burned into the cell at around 900 degrees. The high temperatures cause the silver paste to penetrate into the silicon, thus creating a reliable electrical contact. The cells are now sorted by power class and optical criteria. A sun simulator tests each cell and assigns them to one of 48 quality categories. In this way, minimum tolerances ensure the delivery of solar cells with clearly defined performance features. In the future, the cells will be even thinner and even more powerful. The production process will continue to be optimized. This reduces costs around the entire production chain right up to the end customer.